During the last lecture, we introduced the set of rational numbers. We deduced that the set of rational numbers is closed under addition, multiplication, subtraction, and division. And we discovered that the set of rational numbers is somewhat deficient in the sense that it does not include in itself solutions of certain polynomial equations with constant coefficients. Which is a deficiency because in real life you always often need to solve such equations. So now let's try to dig a little bit deeper into what this deficiency means, and we will try to repair it to further extend the set of rational numbers to something to a larger set that is going to be more usable. So this will provide us with a hierarchy of numbers. Remember, we started with counting numbers and natural number or counting coordinate numbers. Then we extended them to integers. Then we extended the integers to rationals. And now we're going to instead extend rationals to reals. I'm not going to actually, there is a rigorous way to introduce real numbers. I'm not going to do that. So I'm simply going to list certain facts without proving them, but hopefully you will see and understand what these facts mean. A fact that I give you without proof is that if I have a rational number, then any rational number can be represented by either terminating or the repeating decimal. And the opposite statement of this for this is also true, that if I have a terminating or repeating decimal, I always can represent it as a rational number. And I'm going to demonstrate this on two examples. One example is very simple, right? If I have a terminating decimal like I do here, then in order to construct a rational number, construct a ratio of two integers, which will give me this number, it is just sufficient to, in this case, multiply and divide this ratio, this decimal by 1000, and you get, of course, a number like this, which is certainly rational. A somewhat slightly more challenging example is a repeating decimal, but it can also be dealt with very easily. So if I have x given to me like this, what this means is this is 3 point, and then 213 with a bar means that 213 will keep repeating itself. So what this actually means is that I have 3.213, 213, 213, etc. And this continues to infinity. So I want to show that this number belongs to the set of all rationals. And the way I'll do it is that I'll make the following observation, that if I take this number, it starts repeating at the fourth decimal. So if I multiply this number by 1000, then I'm going to get 3213, and then the decimal part is still 213, 213, 213, because 213 repeats itself infinitely many times. So what I got is 3213.213 period. Well, but then if I take 1000x and I subtract x from it, that of course is 999x on one hand, but on the other hand it is 3213.213 period minus 3.213 period. So then the decimal part will go away, and you just have a difference between two integers, which will give you 3210. And so therefore x is a ratio of 3210 over 999, which I get by solving this equation here. So that's a rational number. And you can imagine that given any repeating decimal, the same procedure as in example 2 will always demonstrate that that number is a rational number. Okay, so then if we think about a set of all decimals, now we see that, now of course I can write a decimal uh, terminating, repeating, and I can also write a non-repeating decimal, right? It's not difficult to do, and I'll do it in a second. So if I have other decimals that are non-terminating and non-repeating, then I can always just include it in my list of possible decimal numbers. And I can call these non-terminating, non-repeating decimals irrationals. And so then if I consider a set of all possible decimals, which will now include rationals and irrationals, then I'm going to get a larger set of numbers that we're going to call the set of real numbers and denoted by a bold-faced letter R. Now, clearly, terminating repeating decimals are decimals, so they must be included in R. So Q is a subset of R. So again, we enlarge the set of numbers that we had in the beginning. Now let's give some interpretation to what we have just done. So if I have x squared equal to 2, then we know that the square root of 2 is not rational. We proved it. And we know that the decimal representation for square root of 2 begins with 1.41, and that expansion cannot be repeating because otherwise square root of 2 would be rational. So then if one tries to list all numbers in the decimal expansion of square root of 2, you'll never succeed, right? Because you have to go all the way to infinity because there is no specific pattern to these numbers. But I can make the following observation. So if I take 1, 1 is certainly less than 1.41, and 1 is rational. 1.4 is less than 1.41, and it is rational. 1.41 is going to be less than square root of 2 because the remainder of a decimal part of 1.41 is going to be something greater than 0, clearly, right? So by looking at 1, 1.4, 1.41, I get rational numbers which are closer and closer to my irrational number, square root of 2. Doing something similar by taking, for example, 1.5, 1.42, I get numbers which are above 1.41, and they're closer to x. So if I can write square root of 2 with higher precision, then again I can repeat this approximation scheme, and in that way I'll get rational numbers that are arbitrarily close to radical of 2. A somewhat simpler example is when we would be to write x to find an irrational number for which we can figure out the pattern according to which the decimal expansion is produced. And the easiest thing to do is to construct a number like this. So I take x, which will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So the decimal part will never end. And for sure, it's never going to repeat itself because the integers keep increasing. So this number cannot be a rational number, so it must be irrational because it's not terminating or repeating, so it has to be irrational. Well, on the one hand. On the other hand, so now if I take a sequence of x's like this, x1 is 1, x2 is 1.2, x3 is 1.23, something is missing here, x4 is 1.234. Then in this case, I'm going to produce numbers that are all less than my x, right? Because I'm cutting off the infinite part of a decimal expansion. And yet, those numbers, as index keeps increasing, those numbers are going to get closer to x. And in fact, so that's what I'm writing here. X minus xk is positive. X is always bigger than any of these xk's. And x and xk match up to the k minus first decimal. So that means that if I subtract them, then the first non-zero that I will see will be at the kth position. So that means that these rational numbers, they're certainly rational because they're terminating decimals, are going to be less than x, and I can make them arbitrarily close to x. But also, if I look above x, certainly y1 equal to 2 is going to be bigger than 1.23 something. Y2 equal to 1.3 is definitely bigger than x because the first decimal number here is 2, and the first decimal, and the only decimal, in fact, in this case is 3, and 3 is bigger. So y2 is larger than x. Then I'll construct y3 in a similar way. I'll take first two integers here to be the same. The third integer is supposed to be 3, but I'm going to make it 4. So y3 is bigger than x. And I can continue in this way. You can just follow the rest of this pattern. And you see that in that case, I can construct a sequence of rational numbers. All y's are clearly rational because they're terminating integers, terminating decimals. And just like in the previous case, the number decimal expansion of x will be matched by the decimal of yk up to the kth position. So just like in the previous case, x is going to be smaller than yk, so opposite to actually what we had in the previous case. But like in the previous case, as k gets bigger, yk gets closer to x. So that means that we can approximate our irrational number x, 1.23456 arbitrarily close by rational numbers, both from above and from below x. So that means that that number that we field, that irrational number that we field, that we added to the set of rational numbers, basically what it does, it fields a hole in a set of rationals, right? So in this case, this is sort of a hole such that I can get arbitrarily close to this hole by using rational numbers, but I can never actually be inside that hole itself because being there means being a non-terminating, non-repeating decimal. So that's what the main problem actually that reals accomplish is that they fill the holes in the set of rational numbers. Okay, so that's good. So that's the difference between the two sets. Okay, so both, just like we define addition, multiplication, etc., on a set of rationals, we can do the same thing on a set of reals simply by specifying the rules, the standard rules that we know of adding decimals, multiplying decimals, dividing decimals, etc. So I can define the operations like that on R, and with some work, I should be able to show that those operations on R is bigger than Q, right? So by defining operations on R, I'm defining operations on Q, and those operations will be exactly the same operations as I defined for Q previously, right? So adding decimals should be the same, adding, terminating, repeating decimals, it should be the same thing as adding rational numbers, and you can demonstrate it. And then you can automatically extend this to non-repeating decimals. And so the moral of the story is that the same addition, subtraction, multiplication, etc., that we defined on rational numbers can be extended to the set of reals. Okay, but then the properties of addition and multiplication, etc., are going to be exactly the same on a set of reals as they are on a set of rationals. For example, if I add rational A and B and I add rational B and A, I should get the same answer. Adding irrational A and or real A and B and real B and A should give me again the same answer. So the properties of arithmetic operations should not depend on the fact whether I am in Q or R. And so those sets are self-sufficient from a point of view of arithmetic operations. So that means that if I have to explain to someone what are the distinctions between properties of R and Q, I should not appeal to uh, arithmetic operations because they work in exactly the same way in both sets. Both sets are closed under all of these arithmetic operations. So that means that the distinction between the two sets actually comes from somewhere else. We already know that one distinction, one deficiency of a set of all rationals, like we said, is that a set of all rationals does not include all algebraic numbers, all solutions of polynomials with integer coefficients. In fact, neither does R, the set of real numbers, because, for example, I cannot take a square root of a negative number in rationals. I have to extend my set of numbers further to complex numbers. But in this case, we're not going to worry about complex. So we observe that R basically gives us many more algebraic numbers than Q does. So the distinction is not in terms of operations, but the distinction is in the fact that Q has holes that elements of R will fill in. And in fact, next time we will discuss a different way in which these holes actually affect the properties of R versus properties of Q. Uh, so R will uh, differ from Q in one additional way, not just in terms of including more algebraic numbers, but in one additional way that I will describe in the next lecture. So for the rest of this lecture, we're going to actually concentrate on things that are common to Q and R. So in particular, I can, just like I said, I can look at the various arithmetic operations on Q and R, and they work in the same way. And so if I can understand structure of Q from a point of view of addition, multiplication, etc., then the structure of R from that point of view is going to be absolutely exactly the same. So that means that I can discuss properties of addition, multiplication, addition, and so on without actually referring to the fact whether I work with R or Q. And so what we're going to do is we're going to assume that we have a set V. So V can be either R of Q. On V, I define addition and scalar and multiplication, addition and scalar and multiplication. And I assume that those are going to satisfy the usual rules. Again, commutative law, whatever, right? There are a lot of different rules that algebraic arithmetic operations satisfy. What I want to do is I want to specify the minimum possible set of rules out of which all other rules are going to follow. And that can be done by using the axioms that I'm going to discuss now, so-called axioms of a field. So let's suppose that we have V with addition and multiplication defined on it. Then I'm going to call V a field if the following axioms are going to hold, if the following properties are going to hold. And I'm going to use that notation that I described in the first lecture that will allow me to write fewer words than I would have to write otherwise. So the first axiom I'm going to call A1, and it is going to be this. If I have A plus B plus C, then that is the same thing as A plus B plus C, and this is going to be true for any A, B, and C in V. This is, of course, an associative law. So I'm going to assume that this is always satisfied. We already mentioned commutative law, so A2. So A here, this capital A, signifies that I'm talking about properties of addition. So commutative law A plus B is equal to B plus A, again, for any A, B in V. Commutative law. Okay. A3. What else should we expect from addition? We should expect that there exists a number 0, such that A plus 0 is equal to A, again, for all A in V. Okay, fine. What else? I will need to define addition, define subtraction. How can I do that? I can introduce a property A4 for every A in V. There exists minus A also in V, such that if I add A and minus A, I'm going to get 0. Right, so that's existence of the inverse. Okay, so that's as far as addition goes. So let's think about multiplication. Similar laws should hold, right? So what should M1 be? If I take A times B times C, this should be the same thing as AB times C. And that is again true for any A, B, C in V. What is this? This is once again an associative law, except that now this is an associative law for multiplication. M2 should be a commutative law for multiplication. What should it be? If I take A times B, this should be the same thing as B times A for any A, B in V. So commutative law. What is the analog of 0 in terms of multiplication? What is 0? I add 0 to A, I get A back. So what should I do in multiplication to get my number back? I need to multiply the number by 1. A times 1 is equal to A for all A in V. Right, so that is existence of 1. And then just like it was a case with A4, we have M4, and M4 existence of an inverse. So for any A in V, such that A is not equal to 0, right? So it's an important distinction with addition. There exists 1 over A in V such that A times A 1 over A, that this is equal to 1. Right, so we have very similar properties for addition and multiplication. A1 through A4 only involve addition. M1 through M4 only involve multiplication, but there also must be something which connects multiplication and addition, and this is factoring, right? So I have DL. I'll explain in a second what this means, what it stands for. A times B plus C. I should be able to distribute. This is AB plus AC. This is true, again, for any A, B, C in V. Why is it DL? Because this is a distributive loop. Okay, so this allows us to specify, this specifies the properties for addition and multiplication. So any set on which I can define addition and scalar multiplication that satisfy these properties from A1 to DL is called a field. So R is a field, Q is a field. Okay, I claim that this is a minimal set of properties that you can define. So let us now discuss how you use these properties to establish other properties of reals or rationals. So we have the following theorem. So the following theorem holds. This is essentially our first theorem in this course, which will allow us to deduce something from something else. Use some initial assumptions to deduce additional properties of the object that you're working with. So I'm going to suppose, so let's call it a theorem. I'm going to suppose that A, B, C here, etc. Any number that I'm using is in V, and V is a field. So V in this case can be a set of rationals, set of reals, possibly it can be something else that we have not really discussed yet, but what is it? V is just a set on which I defined addition and multiplication. And V is a field, so then the following is true. Number one, what if I take A plus C and it is equal to B plus C? What should follow from this? It should follow that A is equal to B, right? Now, that is not one of my A1 through DL. That's not one of those properties, but I should be able to deduce this property 1 from my axioms of the field. Number 2, if I take A and I multiply it by 0, I should get 0 for any A, right? Again, this is not listed in my properties. I only know how to multiply A by 1 and how to add 0 to A, but I have not told you what to do with A times 0. Okay, number 3, if we take minus A and we multiply B by it, this is the same thing as minus AB. Number 4, if we take minus A and you multiply this by minus B, you're going to get AB. If you have, similar to number 1, if you have AC equal to BC and C is not equal 0, then A is the same as B. If AB is equal to 0, then A is 0 or B is 0. And okay, that's plenty. So we now want to prove some, if not all, of these properties. And I'm going to do that in the next part of this lecture.